Oh, here's the key point. Something that we don't intentionally practice as homeschoolers frequently is note-taking. So everyone get a blank piece of paper and a pencil and practice reasonably good note-taking today. I'll try to write on the board. You guys will try to write on the paper and just really try to focus on taking good notes. So while you get that out, think through, what is a wave? Okay, I like oscillation. A wave is an oscillation. Does it have to be of air? No, it does not have to be of air.
Air or water or land.
Does it have to be of a medium?
Yes.
For sound, yes. How about light?
No.
Okay, so we don't necessarily even have to oscillate a medium. There are waves that do and waves that don't have to oscillate mediums. So we're not going to put that part in our definition of general wave, but we'll definitely include that part on sound wave because sound waves do have to oscillate a medium. So if it doesn't always oscillate a medium, what else do waves always do besides oscillate? Okay, they do always have a wavelength. But like, what's the purpose of a wave? What does it do?
It carries something.
What is that something?
Sound.
Sometimes.
Light.
Sometimes.
Water.
Who just said that?
He said energy.
Energy, that's it. All right, so an oscillation that carries energy. That's as general a definition as we can get for a wave that really tells us something useful, okay? But then we can break down into different kinds of waves. The first kind of wave that we kind of briefly looked at last week was the transverse wave. This is like a light wave, and it looks something like this, right? So a transverse wave is like a sound wave. It's not like a light wave, and you don't want to in any way think that it is, because we're really talking today about sound. Transverse wave is like a light wave. If I took a rope and I flopped it up and down like this, it would imitate a transverse wave. So what characteristics can we spot about a transverse wave?
You have a crest at the top.
Okay, we've got a crest.
You have a trough.
We've got a trough.
And then there's the amplitude.
The amplitude is from the midpoint to the top. I don't even know how to fit that in there. Amplitude. Anything else?
There's a wavelength.
A wavelength. So we could measure that crest to crest or trough to trough, or we could do it like from right here to the similar part of the next wave, which would be right here. That's wavelength. GTH. Okay, the wavelength. Most people tend to do it from crest to crest, like that. Trough to trough is fine, midpoint to midpoint, as long as you get one whole up and down wave cycle. It doesn't matter what point you choose. One whole up and down wave cycle is one wavelength. So, for light, those characteristics of the wave mean certain things that you'll learn next week. For sound, what kind of wave is a sound wave? Like a slinky wave, longitudinal wave. It's like a slinky. So you have close together parts and spread out parts and close together parts and spread out parts of the slinky wave. Last week we played with the slinky. We sent waves up and down it so you could kind of picture in your mind. Now what's the difference between the transverse wave that travels like this and the slinky wave that travels like this? How could you describe that difference? Because those are definitions that appear on the test, for example. Matt?
Longitudinal waves, oscillations are parallel to its direction.
All right, oscillate parallel.
Versus perpendicular to its direction.
All right, so longitudinal wave will oscillate parallel to its direction. Transverse is perpendicular. Oscillates perpendicular to direction of travel. All right, so it's easier to draw a transverse wave. These slinky waves are just really hard for me to draw. So if a transverse wave is going this way, it oscillates perpendicular to the direction it's traveling, right? A slinky wave is traveling this way, it also oscillates that way. So it's going like this, essentially, right? And now I'm going to just completely erase transverse waves from everything, because I think you probably have a definition of transverse wave on the test, but I don't want you to think about them beyond that, because sound waves are longitudinal waves, and getting that settled in your brain is really important. So sound waves oscillate parallel to the direction of travel, which really makes sense because they're striking your eardrum, right? Your eardrum doesn't oscillate up and down. If the sound waves are going into your ear, it oscillates in and out. So longitudinal waves can make your eardrum go in and out the way that it needs to set off that reaction of, bones moving, liquid sloshing, little nerve cells being whooshed around, and then communicating that to your brain. So, when you're thinking of sound waves, what are the parts of the wave where the slinky is squished together called?
Compression.
Compressions. And the spread out parts?
Rarefaction.
Rarefaction. So, the squish parts are compressions, the spread out parts are rarefactions. There are some, now Bethany, you were all the way up to this point in the beginning. There are some characteristics of waves that relate to how we interpret sounds that we hear. And you mentioned one.
How we hear?
Well, one characteristic of sound waves.
Not they can be higher or lower pitch.
Yes, and how do you know if a sound wave is a higher, what is the characteristic that tells that it's going to be a high pitch wavelength or frequency? So, and I made a note over here already as I was sort of fooling around. So if you have a big frequency, you're going to have a high pitch, but you're going to have a small wavelength. And last week we blew into a kind of full little bottle and a kind of not so full little bottle. This week we have official pipes, right? So when you blow across the top of the pipe to make a sound, that sound is made by what happening? All sound is made by something doing what? Vibrating. The sound is made by vibrations, and what's going to vibrate?
The pipes.
And then the pipe is going to vibrate what? Like, what am I moving when I blow? The air, a column of air. So which pipe will have a taller column of air? The taller pipe. Yeah, okay. So picture, as I blow in, we're oscillating a column of air. The taller pipe has a taller column of air. The shorter pipe has a shorter column of air. And wavelength is quite literally a length. I mean, it's measured in meters or centimeters or nanometers, just like you'd measure the distance from me to Maddie or something. So when you measure a wavelength, like I'm going to start right here at the beginning of a rarefaction, and I'll go to the end of this rarefaction, and that's the wavelength of this longitudinal wave. I could have started at the beginning of a compression and gone to the beginning of a compression. Just have to pick two analogous points on the wave. So that's the wavelength. So when I oscillate a column of air with a long length, then I will have a big wavelength. And you know the equation, frequency is proportional to wavelength based on the speed of light. They're inversely proportional. So if wavelength is big, then frequency will be small, right? If wavelength is big, frequency will be small. That's a key point to know. If wavelength is big, frequency is small.
Yeah.
Okay, so, obviously, conversely, if wavelength is small, frequency is big, right? And frequency is the thing that goes hand in hand with pitch. Okay, so big frequency is high pitch, right? So if frequency is big, it's a high number, right? High number of frequency sounds like a high pitch to us, right? And low frequency sounds like a low pitch. So what do you predict? Will this have a higher pitch or will this have a higher pitch?
The shorter one will have a higher pitch.
Okay, so he says shorter one will have a higher pitch. He says longer one will have a higher pitch. So let's think. If I pick the big pipe, I'll have a big column of air. So that's a big wavelength, right? Big column of air is big wavelength. So that means little frequency. A little number of frequency will give me a low pitch. Right, so the big pipe will give a low pitch. Touche?
If you were to blow in, wouldn't that affect the amplitude instead of the wavelength?
No, and I'll show you in just a second. So frequency-wise, I'm going to have big number, high frequency, high pitch on the little pipe, and low frequency, low pitch on the big pipe. Low pitch, high pitch, low pitch, high pitch. Okay, and it doesn't matter what the pipes are made out of, but it just matters the length of the column of air that's vibrating. So make sure you either understand or somehow memorize high frequency is high pitch. High frequency is little wavelength. They're inversely related according to the speed of light. Speed of sound, velocity, sorry.
Skipping to the next module.
Right. Yeah, speed of how about the velocity of those two pipes? Like the sound, speaking of, which one would have faster or slower velocity? Yes, same velocity, because why?
Because they're both sound waves, and sound has the same speed.
Right, unless I change the temperature of the air, right?
Right.
But since it's the same air, same room, same velocity. All sound waves have the same velocity regardless of their frequency or wavelength. Now, who brought up amplitude? How would I change? When I change the amplitude, I'm not going to change the frequency. But what am I going to change?
The volume.
The volume. When I change the amplitude, I'm going to change the volume. So, little amplitude, big amplitude. Okay, so loud sounds have a big amplitude. And of course, conversely, small amplitudes have a soft sound. So you can have the same, or hopefully sort of the same pitch, since I can't quite blow the same pitch at different volumes, but you have essentially the same pitch but different volume by changing the amplitude. I can't really change the wavelength or frequency unless I change the length of the pipe. Right? That's
How would you find the amplitude in a longitudinal wave?
the amplitude, yeah. So it's how squished the compressions are, basically. I don't think anybody will ever really ask you that, but it's like the magnitude of compression. It's so hard to picture, but like if you picture a slinky, like if you have, it's hard to picture for us, I think. It's the magnitude of compression. So, change sheet. So I really want you to picture slinky waves when you think of sound waves and not transverse waves because they are longitudinal. We'll talk about transverse waves finally next week, which are kind of more fun, or at least intuitive for me. So at the same air temperature, velocity is constant for sound. Don't be fooled by any question that asks you if those waves are in the same air, they're going to have the same velocity if they're both sound waves. Don't be fooled, okay? And you know that equation, and we went over this last week. Is it 0.6?
No, 0.5.
0.5. Memorize equation. Times 0.06 0.6 of the temperature, and that's going to give you the velocity of sound in a given temperature of air. So you can find that. And we just also talked about this equation you need to memorize, this equation you need to memorize, and that last one is just distance equals rate times time. So when we go outside to measure the speed of sound, hopefully later, the distance between us, right, divided by the time between when you see it and when you hear it is going to be the speed, the rate, the velocity.
The top equation is frequency is equal to the speed over wavelength.
Yes. And you can rearrange that. You could just say velocity is frequency times wavelength. And then you can see if velocity is constant, if frequency goes up, wavelength has to go down, right? They're inversely related.
Thank you.
Sure. So that kind of covers stuff from last week in general. This week we want to talk about the Doppler effect. Everyone's taking notes, practice taking notes. That is something I really need to work on more with you guys, because it's not something that I see a lot of. It's a good thing to learn before you get into really hard high school classes. So the Doppler effect. So here's what I want you to picture. Picture the board as a pool of water, right? If it were laying flat, I mean, obviously it's not going to sit on the wall like that. If the board's a pool of water, and let's say I've got a little bug or somebody's bobbing something up and down and oscillating the water. Well, any sort of oscillation like that, that's periodic, a constant rate of oscillation is going to produce what? Waves. Okay, so in water, those waves will spread out. And hopefully that I'm drawing concentric circles. My circles aren't perfect. But essentially, you can see that as you oscillate and you make these waves, let's say our little bug here in the middle, since we have bug problems today, our little bug here is bouncing up and down in one place, right? Those waves are transmitting energy. And because those circles stay concentric, as the water is oscillated, you can see the velocity is constant because the medium is constant, right? Unless the water changes temperature somewhere. Will the sound go faster in water or air?
Water.
Water. Why?
Because sound travels faster in liquid than gas, and faster in solid than liquid.
So sound is faster in denser media. Why is that? Second?
I was going to say because it doesn't use as much energy to travel through a medium like this or through water as it does through air.
It's not necessarily energy because the wave is still transmitting the same amount of energy. But what is it doesn't need as much of? Shane?
It doesn't have to take as long to hit the atoms.
Yes. So it's time. It's a time issue. How far apart are air molecules? Really far apart compared to liquids or compared to solids, right? So for a wave to pass through air molecules, it has to take the time from when this one is hit with energy till it finds some next one to hit with energy, and it finds the next one. There's a big distance between, so they take time. But in liquid, those molecules are much closer together. The time between this one getting hit with the energy and then transferring the energy to the next one is much smaller because the distances are shorter. And solids, of course, are packed right together, so the sound travels very fast in solids because the energy passes from thing to thing very fast when they don't have any distance to collide. You look skeptical.
No, that's not what it is. It is, no,
You're in pain.
what?
You're in pain.
No.
Okay.
It was,
So,
I was just rubbing my eyes.
okay. Sound travels faster in denser media. But here we are, our bug is oscillating the water. The velocity is constant since the circles are concentric. So let's think about frequency. Let's say I'm dunking my hand in the water right here, right? And one wave is hitting my hand per second. What does that tell me about?
The frequency.
The frequency. So frequency, let's say, in this situation, if one wave is hitting my hand per second, then what would that be called? Like, what unit do we actually call that? One wave per second.
Hertz.
1 hertz. 1 hertz. Or, I mean, you could just say 1 over a second, like that. 1 hertz, I don't know, just seems tidier. But a hertz is really a 1 over a second, because a wave's not really a unit. But I want you to think of it as a wave per second when you're thinking of frequency, because just 1 over seconds isn't a really meaningful thing unless you consider it that way.
I apologize for the interruption. We're sending a thank you card to Cornerstone